So my name is Nicholas McCarty, and I'm a second-year student, and I'm a microbiology major, but I actually do biochemistry research in Professor Dale Abel's lab. And essentially we look at the molecular mechanisms that lead to heart failure in the context of diabetes. So to give you guys a little bit of background on how insulin works in your body, insulin is produced in beta cells in your pancreas, and then they circulate throughout your bloodstream and they bind to virtually every cell in your body. And what we did here is we generated what's called a cardiomyocyte-specific knockout of IRS1 and 2. So the way this works is insulin binds to insulin receptor and insulin-like growth factor 1, and this phosphorylates insulin receptor substrates 1 and 2, which then go on for this downstream signaling cascade, and there's all kinds of cardiovascular regulators that come about. And what we did is only in the heart, we knocked out IRS1 and 2. So essentially we're completely disrupting your insulin signaling, and then we wanted to see what happens. And the first thing we did is something called transthoracic echocardiography, and it's like an ultrasound. You put something up to a mouse's heart, and you can watch its heartbeat in real time. And we did this at several time points. So we did pre-induction of the transgene, so like pretty much wild-type mice, they don't have anything wrong with them. And then we did it at 3 days, 1 week, 4 weeks, and 6 weeks after we knocked out these genes. And you can see that in the knockout mice, we see this huge hypertrophic effect. So their hearts are swelling, their hearts aren't beating anymore. And we said, hey, we have something really cool here, but what's the mechanism, right? Like why is insulin signaling so important for your heart? And the next thing we did is we looked at this tissue under a microscope essentially, and we took pictures. And this is actually cardiovascular tissue after 3 days, 1 week, and 4 weeks. And in the knockout mice, without these genes, you see the stretching and tearing of the actual muscle. And this is important because right now, if the prevalence of diabetes continues to expand, by the year 2050 in the United States alone, there's going to be 80 million diagnosed diabetics. And 65% of these people who die of diabetes-related causes die because of heart failure, so their hearts aren't functioning properly. So this study is essentially serving as a model. We can say, hey, what happens when you don't have insulin signaling, or when that signaling is disrupted, what's going to happen to your heart? And if we have a more in-depth understanding of the molecular mechanisms that come about as a result of this model, we can say, okay, are there alternative pathways that could regulate AKT and mTOR without insulin signaling? Because right now the current treatment for diabetics is just to inject them with more insulin. So late stage diabetics, the current treatment is more insulin, more insulin, more insulin. And this is actually increasing the progression of heart failure. So these diabetics have a worse prognosis at life. So right now, a lot of research is going into finding alternative pathways that could regulate this without using insulin at all. So thank you very much.